Hello, everybody. So, uh, regarding the electrical power system 2, I started at the beginning the normal operation of the system. So I told you how we can calculate the um, power flow and how many which method is better to be used to find out the power dispatch from all of the uh, components and generally uh, we talk about the optimal power flow and so on. So in the second uh, part of the this course, I talk about fault analysis. I told you how many faults do we have and how we can analyze the fault in in the power systems. And then we want to talk a little bit about power system stability. So welcome to lecture 8 of electrical power system 2, which focus on power system stability. And in this lecture, we will study how a power system remain in a stable operating condition when they face disturbances such as sudden load changes or short circuits or generator outages and so on. On the other hand, we want to see that you can assume that we receive a fault. So how the systems can be remain stable if we have a fault, and we will learn the basic concept of stability, why it is important for reliable electricity supply, and how generators and transmission systems respond to faults. So the lectures will also introduce different types of stability, including steady state stability, transient stability, and dynamic stability, along with the main factors that affect system performance and security. So in a well operating power system, conditions involve smoothly over time in a predictable way. Although loads and generators are continuously changing, these changes follow expected patterns such as load behavior matching forecasts and generators being scheduled and brought online as planned. Network topology may also be adjusted in in a control and planned manner while all system variables remain within their normal operating limits. So under these conditions, there are no unexpected outage and faults or sudden disturbances in generators or network components, and the systems can therefore be considered to be in a Gaussian steady state condition. In this state, the system behavior is typically analyzed using algebraic power system and uh, um, power systems equations rather than the differential equations, since dynamic effects are minimal and the focus is on steady operating conditions. Okay, however, in real power system, unexpected events can disrupt normal operation and lead to instability. So faults may occur on transmission lines, transformers, or buses, causing sudden disturbances in voltage and current flows. And generators can also fail unexpectedly, removing a significant source of power from the systems. In modern power systems, rapid and unpredictable changes in renewable energy production, such as sudden drops in wind or solar output, can further affect system balance, and at the same time, Unexpected increases in electrical demand can place additional stress on the network. So in both, so unexpected rapid decrease in or reduce in renewable production, or unexpected rapid increase in load demand. Uh, sorry, um, and all of these events can push the system away from its normal operating condition and create several challenges for maintaining stability and security for us. Okay. After such a contingency, a well-designed power system does not immediately become unstable. Instead, it is planned and operated with sufficient safety margin to so that it can observe disturbances, and the system typically shifts to a new stable operating point that still satisfies operational constraints even through conditional conditions may have changed, and system operators then take corrective actions such as redispatching generation or adjusting network settings to restore the required security and reserve margins. And once the system is stabilized, it is again ready to withstand another possible contingency. In practice, this continuous cycle of monitoring and control is weak uh, is what keeps the system reliable, even if it is less dramatic than what is usually shown in movies, you know. Okay. In some cases, contingency can exceed the design's assumption of the power system and lead to more serious conditions. This may happen during extreme weather events such as severe storms where multiple transmission lines are disconnected simultaneously, and it can also be worse um, uh, um, worse by human errors, either in operational planning or in operational planning or during system operation, where incorrect decisions or assumptions contribute to the disturbance. And an example from the other complex injury systems in the Costa Concordia disasters recently happened, which highlights how system level process rather than a single individual are often responsible for failures. In um, in addition, contingency can become more severe if protection systems do not operate correctly. For example, when a fault is not clear quickly, or when more network components are disconnected than necessary. So these combined factors are significantly increase the risk of system. So if the system is unable to recover after a severe contingency, it may become unstable, and in such situation, protection systems will act to disconnect additional equipment in an attempt to protect the network, and this can sometimes lead to cascading outages where one failure triggers further disconnections across the systems. And in extreme cases, this process can result in a partial or even complete system collapse. So recently, commonly known as a blackout. So you probably heard about the total blackout in Spain last year. So all right. A partial, sorry. A partial collapse occurs when circuit breakers isolate the affected part of the network and preventing the disturbance from spreading further. If the balance between the generation and load can still be maintained in the remaining system, then the unaffected part continues to operate normally, avoiding a total blackout. Okay, an equilibrium state of a power system is a condition in which the system variables remain constant over time unless an external disturbance occurs. So in this state, the system is balanced and no internal changes take place here, and solving the power flow equation allows us to determine this equilibrium for a given set of loads and generation levels, providing a steady operating point of the system. However, when there is a change in load demand or generation output, the equilibrium point of the systems also shifts to a new operating condition. A key question in power system stability analysis is whether this new equilibrium is stable, meaning the system can return to it after small disturbances without losing synchronism or violating operational limits. Okay, a power system is considered stable if after a small disturbance its state variables return to a normal operating conditions or settle to a new acceptable equilibrium. In general, we describe the system using a set of state variables denoted by x, which represent quantities such as rotor angle, speeds, voltages, and other dynamic elements of this network. Stability means that when these variables are slightly disturbed, their trajectories remain bounded and do not diverge over time. So if the system is stable, if naturally resists small disturbances and returns to equilibrium without losing synchronism or violating operational limit. So you can see here a very simple graph. You can see if this ball is going up or down, coming back to this point again. So if it is unstable, the state variables drift away, potentially leading to system collapse. Okay, a useful way to understand stability is through the idea of potential energy. In a stable power system, the operating point corresponds to a state of minimum or locally minimum potential energy. When a small perturbation occurs, the system is temporarily pushed away from the equilibrium state. However, because the system is stable, internal factors act to restore it back toward the original operating point. So as a result, the state variables oscillate slightly, but eventually settle again at the equilibrium. So this return to equilibrium behavior is a key characteristic of stability and reflects the system's ability to observe disturbances without losing control or synchronisms. Okay, in an unstable system, the equilibrium point does not act as a restoring condition for a system after disturbance. Using the potential energy concept, the operating point may correspond to a peak or an unstable configuration rather than a minimum. When the system is slightly perturbed, instead of being pulled back toward equilibrium, the state variables continue to move away from it. This leads to growing deviation over time, such as increasing rotor angle separation or voltage collapse. So as a result, the system cannot maintain synchronism or acceptable operating conditions, and instability develops. So this figure is showing very easy to understand these concepts. Okay, in an unstable system, even a small perturbation is enough to push the system away from its equilibrium point. So instead of being restored back to its original operating condition, the system diverges from it over time. So this means that the equilibrium itself is unstable and the system cannot remain close to it after disturbance. So as the state variables continue to move away, the system may experience increasing oscillations, losses of synchronism, or voltage collapse. So ultimately, this leads to the inability of the system to maintain normal operation, confirming that the equilibrium point is not stable. Okay, in a stable power system, changes in operating conditions do not cause abrupt or uncontrolled behavior. Instead, let me add a student. So instead, the system evolves gradually from the original equilibrium point to a new one as a condition such as load or generation change. So this process can be interpreted using the concept of potential energy, where the system is mostly transitions between the different stable minima. So as the operating point shifts, the state variables adjust in a controlled manner without diverging or losing stability. Eventually, the system settles at a new equilibrium that corresponds to the updated conditions while still maintaining secure and acceptable operations throughout the transition. You can see that we can have in some systems, we can have different uh, minimal point. So, and this is the original conditions, and this is a new condition. So it will be change. Okay. Uh, a steady state. Let me. Okay. A steady state stability refers to the ability of a power system to maintain synchronism and return to its equilibrium point after small gradual disturbances under normal operating conditions. And in terms of the potential energy concept, a stable operating point corresponds to a local minimum where the system naturally tends to remain. However, if system conditions change significantly, the operating point may shift to a region where this restoring property is lost. So, in such a case, even a small perturbation can prevent the system from returning to equilibrium, indicating instability. This means the system has evolved to a condition where it can no longer maintain steady state stability, and its normal operation is no longer secure. So transition stability. So let me, yes. In transient stability analysis, a key question is how large a disturbance the systems can withstand before it becomes unstable. So this is often interpreted using the concept of potential energy and stability margins. A large disturbance pushes the system far away from its equilibrium point, and the system ability to remain stable depends on whether it has sufficient stability margins. So the stability margin represents how much distance exists between the normal operating point and the boundary of um, instability. You can see here stability margin. So um, this is large perturbation. So we can, uh, if this ball is going this way, and then it will uh, falling down to the unstable margin. So the stability margin represents how much distance exists between the normal operating point and the boundary of instability. If this margin is large enough, the system can survive even severe perturbations and still return to a stable operating conditions. However, if the margin is small, a large disturbance may cause the system to lose synchronisms and become unstable. Okay, uh, steady state stability and transient stability are closely related but fundamentally different concepts. Steady state stability depends only on the characteristics of the systems and its operating state, and it describes the system ability to remain stable under small continuous disturbances. In contrast, transient stability depends on not only on the system and its initial state, but also on the magnitude and nature of the disturbance. In theory, any system can become unstable if the perturbation is large enough. For this reason, stability studies are usually limited to credible or realistic disturbances, which represent the types of faults or events that are expected to occur in practice. So this approach ensures that system design and operation focus on conditions that are most relevant for reliability and security. Okay, stability limits define the boundary between secure and insurance operation of a system, power system. For steady state stability, the main concern is whether the system can continue operating without collapse following relatively small but significant changes, such as the disconnection of a transmission line or a generator. And for transient stability, the focus is on the system's response to large sudden disturbances such as a short circuit fault. In this case, the key question is whether the fault will push the system behind its ability to remain in synchronism, leading to instability. In both cases, stability limits help determine, sorry, determine how much disturbance the systems can tolerate while still maintaining reliable operations. So we have here in these two figures steady state stability and transient stability. So the stability of a power system refers to its natural ability to develop restoring forces that are equal to or greater than the disturbing forces, so that the system can maintain its equilibrium state. In particular, if the synchronizing factor forces that keep synchronous machines operating together are strong enough to overcome the effects of the disturbances, the system is said to remain stable and in synchronism. The study of stability is therefore mainly concerned with understanding the behavior of synchronous machines following a disturbance and determining whether the system can successfully return to or maintain synchronisms under such conditions. So steady state stability refers to the ability of synchronous machines to remain in a synchronism when the load is increased gradually over time. It is mainly concerned with determining the maximum loading limit that the machine can support without losing synchronisms under slow and continuous changes in operating conditions. But dynamic stability, on the other hand, deals with the system response to small disturbances that cause oscillations in the system variables. A system is considered dynamically stable if these oscillations remain bounded and decay quickly over time. If the oscillations increases in amplitude instead of dying out, the system becomes dynamically unstable. These types of instability is often associated with interactions between different control systems within the power networks, which can amplify oscillatory behavior if not properly damped. Okay, transient stability refers to the ability of a power system to maintain synchronisms when it is subjected to large disturbances. These disturbances can cause significant and rapid changes in rotor speeds, power angles, and power transfers across the network. Transient stability is a fast dynamic phenomenon that typically occurs within a few seconds after the disturbance. Common examples of such disturbances include the occurrence of a fault, the sudden outage of a transmission line, or the abrupt application or removal of large loads. So transient stability studies are therefore essential to ensure that the power system can survive the immediate post-fault conditions following a major disturbance and continue to operate in a stable manner. All right, here I want to say that transient stability studies are typically carried out during the planning stage of new generating stations and transmission systems. These studies play an important role in ensuring that the power system will remain stable under severe and realistic disturbance conditions before the system is actually built or expanded. They are useful in determining several key design and operational requirements, including the type and settings of the protection relaying system needed to safeguard the network. The, they also help in identifying the critical cleaning time of the circuit breakers, which is the maximum time allowed to clear a fault before the system becomes unstable. In addition, uh, transient stability studies are used to evaluate voltage levels across different parts of the system and to assess the power transfer capability between interconnected systems. These factors are essential for ensuring secure and reliable system operation under fault conditions. Okay, power system stability is mainly concerned with the rotor stability of the synchronous machines, since rotor angle behavior largely determines whether the system remains in synchronisms after disturbance. So to simplify the analysis, several assumptions are commonly made. First, the system is assumed to be balanced, meaning that only balanced three-phase conditions and balanced disturbances are considered. Second, deviation of machine um, frequencies from the synchronous frequencies are assumed to be small, which allows linearized or simplified dynamic models to be used. So third, the network and impedance loads are assumed to be in a steady state during the analysis period so that voltages, currents, and power flows can be calculated using power flow equations. These assumptions make it possible to study stability in a tractable and practical way while still capturing the essential system behavior. Okay. The European incident of 4th of November 2006 refers to a major interconnected power system disturbance that affected several countries across Europe. So it begins with a planned disconnection of a transmission line in Germany, which under normal condition was expected to be safe. However, due to unexpected power fluid redistribution and insufficient coordination, the system experienced a cascading series of outages across the network. So this led to widespread power interruptions affecting uh, so many millions of customers in multiple European countries, and they even highlight the importance of coordinated grid operation, accurate load flow prediction, and robust interconnection management in maintaining system stability in large interconnected power systems such as the European blackout of 4 November 2006. And during the European incidents of 4 November 2006, a transmission line in Germany was internationally disconnected to allow a large ship to pass safely under a river crossing. So this planned action was expected to be within normal operating limits. However, the disconnection caused an unexpected redistribution of power flows across the interconnected European grid. As a result, other transmission lines become overloaded and were subsequently disconnected by protection systems. So this sequence of events initiated a cascading effect within the network, demonstrating how a single planned switching action under certain conditions can lead to widespread instability if system conditions are already close to their limits. Okay, the European incident of 4 November 2006 illustrates how tightly interconnected modern power systems can be vulnerable to cascading failures. What initially began as a routine and planned switching operation quickly escalated due to unexpected power flow redistribution and overloads on neighboring transmission lines. Protective devices then acted to disconnect additional lines, which further increase stress on the remaining network. So this chain reaction led to a widespread disturbance affecting large parts of Europe and demonstrated the importance of accurate system planning, real-time monitoring, and coordinated control actions in maintaining stability in large interconnected grids. Okay, following the system separation in the European disturbance of 4 November 2006, the interconnected grid split into different electrical areas, each experiencing its own frequency evaluation. So because generation and load were no longer balanced across the entire system, each area showed a different frequency deviation depending on its local surplus and or defect of power. Areas with excess generation tended to experience a rise in frequency, while areas with higher demand than supply experienced a drop in frequency. So these frequency deviations were not instantaneous but evolve dynamically over time as control systems and protective actions responded to the disturbances. So the overall behavior highlighted how system separation leads to independent frequency dynamics in each islanded part of the network and emphasizing the importance of maintaining balance within each control areas after larger scale disturbances. Okay, electromechanical stability, commonly referred to as transient stability, describe the dynamic interaction between the mechanical and electrical components of the power system. The mechanical system consists mainly of the rotating masses of synchronous generators which supply mechanical power through their prime movers. The electrical systems represent the network that transfers this generated power to the loads. These two systems are strongly coupled through the generator's electromagnetic torque and rotor dynamics. And when disturbances such as a fault occurs, this coupling is disrupted, leading to an imbalance power between the mechanical input power and electrical output power. And the the key question is that here is that in electromechanical stability analysis is how the combined system responds to such a fault and whether the generators can maintain synchronisms and return to stable operating condition after the disturbance is clear. Okay, here a synchronous generator can be represented using a simple mechanical model based on torque balance. The generator develops an electromagnetic torque Te while rotating at synchronous speeds or omega m. The prime mover supplies a mechanical driving torque Tm. So under steady state conditions and neglecting losses, the system is in equilibrium, meaning that the mechanical input torque is exactly equal to the electromagnetic output torque, which is we have this equation. This balance ensures that the rotor continues to rotate at constant synchronous speed without acceleration or deceleration. Okay. Um, the dynamic behavior of a synchronous generator can be described using Newton's law of motion applied to rotational systems. The rotor's motion is characterized by its angular position, theta m, while J represent the combined moment of inertia of the prime mover and generator. According to Newton law, the difference between the mechanical torque Tm and the electromagnetic torque Te produce an accelerating torque that determines the rotor's angular acceleration. So the fraction of d d2 theta m over dt, the second derivation of theta m based on the time is equal to Tm minus Te. So this equation forms the basic for analyzing the dynamic response of the generator during the disturbances. Okay, the swing equation is a fundamental relation used to describe the dynamic behavior of a synchronous generator. In this equation, theta m represent the angular displacement of the rotor with respect to a fixed reference axis on the stator. It is based on a basic principle of rotational dynamics, which states that the accelerating torque acting on a rotating body is equal to the product of its moment of inertia and its angular acceleration. Okay, in this context, both the mechanical torque Tm and the electromagnetic torque Te are taken as positive for a synchronous generator. The swing equation therefore provide the basis for analyzing how the rotor angle changes during the disturbances in the power systems. Okay, this means that the mechanical torque Tm represent the resultant shaft torque that tends to accelerate the rotor in the positive theta m direction of the rotation. And in a generator, this occurs when the mechanical input exceeds the electrical output, leading to acceleration of the rotor. The direction of torques and rotation can be understood by comparing generator and motor operations. In a generator, the mechanical torque acts to drive the rotor forward, while the electrical torque opposes this motion. In a motor, the situation is reverse, where electrical torque drives the rotor and mechanical torque acts as a load. So these relationships are illustrated in these two figures, showing the direction of rotation and the interaction between mechanical and electrical torques for both generator and motor operations. So under a steady state operation of a synchronous generator, the mechanical torque Tm and the electrical torque Te are equal. As a result, the accelerating torque Ta becomes 0. In this condition, there is no net acceleration or deceleration of the rotor, meaning the rotor speed remains constant. This constant operating speed is the synchronous speed, which ensures that the generator remains in synchronism with the power system. Okay, this slide illustrates the angular relationship between the rotor field and different reference frames in a synchronous machine. The rotor field is shown rotating at the synchronous speed WSM, uh, aligned with the reference rotating axis. The angle delta M, known as the rotor or load angle, represent the displacement between the rotor magnetic field and the synchronously rotating reference axis. Meanwhile, theta m indicates the position of the rotor field with respect to a fixed stationary reference axis. This distinction is important because electrical machine analysis is often simplified by using a rotating reference frame that moves at synchronous speed, making the rotor field appear stationary in the frame. Understanding these angular relationships is essential for analyzing torque production, stability, and dynamic behavior in synchronous machines. Okay, since we are increased in the rotor speed relative to synchronous speed, it is convenient to express the angular position in a synchronous rotating reference frame. So this reference frame moves at constant angular velocity, omega Sam, and the synchronous speed. In this case, the rotor angle can be written as this equation, where delta m represent the initial rotor position at time t is equal to 0, measured with respect to the synchronously rotating reference frame. This representation helps separate the steady synchronous rotation from the dynamic deviation, which is essential for studying system stability. Okay, taking the time derivative of the rotor angle expressions gives the rotor angle velocity. So starting from theta m is equal to omega Sm t plus delta m. So we have this equation. We can derive from two sides. So omega m is equal to this equation, and this shows that the rotor speed consists of the synchronous speed plus a small deviation term. Similarly, taking the second derivative gives the rotor angular acceleration. So we can take the second derivatives second derivative of theta m versus the t is equal to second derivative of delta m. So this indicates that only the deviation angle delta m contributes to acceleration, which is the key variable used in transient stability analysis. So in steady state operation of a synchronous generator, the mechanical torque Tm is equal to the electrical torque Te. As a result, the net accelerating torque is 0. So Tm minus T is equal to 0. This means that there is no angular acceleration and the rotor speed remains constant. So um, is equal to Wm. This is a constant. So this constant speed is synchronous speed. Therefore, the rotor angle evolve linearly with time as theta theta m t is equal to omega m synchronous plus theta m0. So we will have these equations. This is a synchronous speed. Okay. When the mechanical torque Tm is not equal to the electrical torque Te, the generator no longer operates in steady state. In this case, the rotor speed is no longer constant, meaning that omega m is not equal to constant, and the system experiences dynamic changes. To analyze this behavior, we need to define the angular deviation from synchronous machine as delta mt is equal to theta mt minus theta m synchronous. This quantity represents how far the rotor angle has deviated from the synchronously rotating reference frame. It is a key variable in stability studies as it describes the dynamic response of the generator during the and after disturbances. Okay, the rotor angle. um okay, the rotor angle deviation is defined as the difference between the actual rotor position and the synchronously rotating reference frame. So delta mt is equal to theta mt minus theta m synchronous. Expanding the synchronous reference gives this one. This is a synchronous reference. And taking the first deviation from two sides, uh, and we will have this one. This is the first derivation from these two sides. This derivation is equal to 0, and this derivation, so t can be removed. So taking the second derivation again, this one will be removed, and substituting into the Newton law leads to the swing equation derivation form like this. And this formation is the basis of transient stability analysis in power system. Okay. Okay, the swimming equation can also be expressed in terms of power instead of torque, starting from the mechanical form. This is a mechanical form, and mechanical and electrical powers are related to torque by this one. Pm is equal to omega mtm. And substituting this expression into the swing equations, we can it can give us this equation. So this form of the swing equation is also widely used in stability studies, as it directly relates the accelerating power difference between the mechanical input and electrical output to the rotor acceleration. Okay. The swing equation can be further expressed in per unit form, which is widely used in power system analysis, starting from this one. J omega d. This is uh, uh, periodic form. So, and then dividing both sides by the generator base power SR rated. So this is a SR rated base power. We can find these equations. So we just need to divide both sides by SR rated. So this per unit form simplified the analysis of different mechanical and systems by normalizing all quantities to a common base. So this is just can be converted to the per unit. Let me, okay. To simplify the swimming equation further, the inertia constant h is introduced, and since the moment of inertia j varies significantly between different generators, so using it directly is often inconvenient for system studies. So the inertia constant h is defined as the ratio of the stored kinetic energy at synchronous speed to the rated megavolt amp of the generator. So H can be calculated based on this equation. Using this definition, the swing equation can be rewritten in a more practical form. So we can uh, just replace h in the swing equation. So the inertia constant provides a convenient way to compare different generators and plays on an important role in determining how quickly a system responds to disturbances. So I want to close my session here in slide 41.